There are lots of characteristics that define a person. But when we want to identify a person, we just don't store all these characteristics, we just store the fingerprints. And for all practical purposes, that suffices, right? It will be very, very difficult to find two people with the same fingerprints. And exactly that is what we want to replicate in computer for storing data. Okay? So basically the motivation comes from this, that you may have large items that you want to store. But that may take up a lot of space, so you don't want to store it entirely. But what you want to do is maybe store a fingerprint of it. Now we have to define what we mean by a fingerprint of a data item. Okay? But this fingerprint should be able to kind of identify the data uniquely for all practical purposes, like our physical fingerprints do. And it is, as you may guess, typically used for avoiding comparisons and transmission of bulky data. Okay? And like, for one example is like, suppose you have a web browser and it is storing some files, and if it may have like large files to store, and then it want to kind of check when this file is kind of updated to update your browser, its copy in your browser. It may just store fingerprint instead of storing entire file, and fetch in fingerprints to check whether it's changed or not. Okay? And as we may guess, I mean, hash functions is one thing we will use for this, because hash functions do really shrink the data, right? Depending on how we choose the hash function, but we can choose hash functions which shrinks the data. Okay, and then because we are actually losing some information, there might be some error probability. But every time we want to bound this error probability and say that it's very, very, very tiny. So that's why it's enough to store those fingerprints for all practical purposes, in quotes. Okay, so let's start with one example for hash tables. Suppose I want to build a hash table which does insertion and lookup very fast. But my objects are very, very weird. They are very big, like graphs, and difficult to store. It will be very difficult to store many of them. So instead what I do is I compute a hash function. So I have an object x, I compute h of x, and instead of storing the entire object at h of x, I just put one bit, 1 or 0. So every position of hash table has only one bit stored. Okay, that's a huge reduction in space. Okay, and now if I want to look up whether object x is there in the table or not, I can compute h of x and see whether the bit is 1 or 0. If bit is 0, then I say it's not there in the table. If bit is 1, then it's there in the table. Now, can I make errors in this? So if I see 0, and I say the object is not there in the table, did I make an error? No, right? Because I make that bit 1 only when I insert x. If it is 0, that means I never inserted x, right? So if it is 0, then it's not there. Suppose I see that h of x is 1. Does that mean that I really inserted x? No, right? Maybe there is another object y, and it so happens, it may happen, right, that h of x equals h of y, and because I inserted y, I set that bit to 1. And that bit is 1 because of y and not because of x. So I may make an error when I say yes, but I never make an error when I say no. So this is one-sided error. Okay? Now, I want to kind of make sure that this one-sided error is very, very low. So far we saw that there are no false negative, but there might be false positive. Now suppose my hash function does this error with probability alpha. How can I reduce this error. So suppose alpha is say half. How do I reduce this error to say 1 over 2 to the 10? Yeah.
Use more than just one bit.
Yeah. So instead of just doing one hash, let me sample 10 hash functions independently. Okay? And every time I insert x, for all those hash functions, hi of x, I put that bit to 1. Now, when I ask whether x is there or not, I compute all of these hix and check whether at each position I have 1, 1, 1, 1, 1. If I have 1, 0, I'll say no. If all of them are 1, I'll say yes. Now the error is what? Alpha to the 10. That is 1 over 2 to the 10. Because I'm assuming here that I'm able to sample very good hash functions independently. So there is mutual independence here. So if I can do that, then I can reduce the error from 1 over 2 to 1 over 2 to the 10, which is very tiny, and we can live with that. Right? So, and that is a huge reduction in space. If every object had like 2 to the, say, 30 bits, then you're reducing those 2 to the 30 bits to 10 bits. Right? So this is one example of you can say that this hash table is a fingerprint, storing fingerprint instead of the objects. And fingerprint is just bits, that's it, 1 bit. Okay, so I don't want to talk about hash tables in this lecture. I want to talk about using fingerprints to design fast algorithms. Okay, finally we are interested in fast algorithms, right? So in particular, I want to focus on this particular problem that you have seen already for FFT. So I have a long string T, let's say bitstring or whatever, and there is a pattern, small pattern P. And I want to see how many occurrences of, not how many, at what all positions this P occurs in T. Okay, so the T is long string. Okay, let's say 2 to the 30 many or whatever. You have a Wikipedia, say. And I want to search, say, algorithms. What all places algorithm appears in this Wikipedia? Copy of this Wikipedia. Okay, and I want to do this fast. Okay, so for this we will discuss this Karp-Rabin randomized algorithm, and for that I will need these things. So first we will discuss how do we sample a prime uniformly at random, which is more than some number, which is at most some number, say x. Okay, so how do we sample primes? Second, we will have to do string equality, and we will do it via mod p arithmetic. So how do we do that? While reducing the error, with minimum error. Okay. Then we will talk about something called rolling hash. Okay, this is Rabin's fingerprint scheme. And then finally, using all these three, we'll design this algorithm, which will be order m plus n, almost order m plus n, under some assumptions, but those assumptions are fine under all practical purposes, actually. Okay, so let's start with sampling problem. So suppose I want to sample a prime uniformly at random between 1 and some number, some integer x. How do we do this? Suppose we want to do this. How do we do this? Any possible procedure. Okay, I'm telling you x, say 2 to the 64. And I want to sample a prime uniformly at random. So there might be a lot of primes between 1 and 2 to the 64. I want to sample one of them uniformly at random. How do I do that? So question is clear?
You list every single prime?
Sorry?
You can list every single prime?
I can list every single prime. How much time that would take? Maybe I'll check every number, whether it's prime or not. I can do that. Probably I may have to go to all 2 to the 64 numbers. That may take a lot of time. Can I do some kind of randomization? I'm fine with some error or some expected running time, either. So what if I do this? I sample some number uniformly at random between 1 and x and check whether it's prime or not. If it is prime, I output it. Otherwise, I just repeat. Okay? So here you have to check whether given number is prime or not. And for that, there are 2 possible methods. One is the deterministic but slow method, which is by Agrawal, Kayal, Saxena. This is one of the very celebrated result in 20th century. And the other is Miller-Rabin randomized primality test. This came before this AKS algorithm. This is very fast, but it is randomized. So it may make some error. So what kind of error? Yeah.
Well, since primes are like more sparsely distributed as numbers get higher, this isn't, does that mean it's not uniform?
We will argue that this will, yeah, you are right. It's not clear that whatever I'm doing actually uniform sampling. It's not clear. But we'll prove it. We will see why it is uniform. And you are right, the primes are very sparse. Okay. So, yeah, so which will output, whenever the P is prime, it will correctly output prime. But when P is not prime, it may sometimes say prime. Even if P is a composite, it may say prime, but with very, very low probability. Okay? So this is fine. I don't want to kind of get stuck here. So you can do, suppose you can do this checking. Given a number, you can check whether it's prime or not somehow. Okay? Now I want to ask the correctness of this algorithm, like you pointed out, why it will give me a prime which is picked uniformly at random. And also the running time. How much, because the primes are sparse, in 1 to x, there will be very, very small number of primes. Right? So how much time would the algorithm take in expectation? Okay. So let's say, so I want to answer this question. Is the return prime sample uniformly at random? Okay. So let's say pi x is the number of primes in 1 through x. I don't know this number. Okay. But let's say pi x is the number of primes that are at most x. I want to prove that if I fix any particular prime p star, which is at most x, which is in this set basically, then probability that algorithm outputs p star is 1 over pi x. If I prove this, then I prove this, then I say that yes for this question. Do you agree? Right? So let's prove it. Let's say A is the event that I pick a prime in one round. So when I'm picking a number p, what is the probability that I pick a prime? It's pi x over x, right? Because there are x possible numbers to be picked. Out of that, pi x are prime, and I'm picking uniformly at random, right? So picking up the probability of picking a prime is pi x over x, right? What is the probability I could pick p star? What is the probability that I pick a particular number, say 1? 1 over? In a round. What is the probability I pick 4? 1 over x. Right? In a one particular round, I am picking one number between 1 through x uniformly at random. Right? So picking any particular number, that probability is 1 over x. Right? So let's say B is the event that I pick a particular number, say p star, and probability of B is 1 over x. And because A is the event that I pick any prime, and because p star is a prime, clearly B is subset of A. right? Because P star is a prime. So then this probability that algorithm outputs P star is same as saying what is the probability that I pick a prime, and condition to that I pick P star. So what is the probability that of B given A? If I just use the formula that we know, it's just probability of A intersection B divided by probability of A. But because B is subset of A, this probability is just probability of B. Right? And if you simplify, you'll get 1 over pi x. So basically, because I am picking a number uniformly at random, picking any prime among the primes is also uniformly at random. Questions? And the running time, that is how many samples do I have to make in expectation before I find a prime? What is the probability that I find a prime in the first go? In the first round. How many primes are there? Pi of x. Total numbers are x. Right? So what is the probability I pick a prime in the first round? Pi of x over x. So if I do, so suppose my random variable x is number of rounds I have to make before I pick a prime, then x equals 1 with probability pi x over x. Now what is the probability I don't pick a prime in the first round? Instead I pick a prime in the second round. What is that probability? That is 1 minus pi x over x times pi x over x, right? Times 2. If you do this series, you will get a summation series. If you simplify it, you will get this x over pi x. You can try and do that. Okay? Good. But how many primes are there? Are these probabilities good or bad? Is the running time good or bad? When I say the running time is, expected running time is x over pi x, is it just x over some constants? Let's say 100, x over 100. That would be equally bad, right? So it is sparse, but not too sparse like x over a constant. It is x over ln x. Okay, log to the base e x. Okay, and this is one of the most prime number theorem. This is called prime number theorem, and it's a very celebrated theorem. It was not that easy to come up with, and this was proved by both of these people, Hadamard and Poussin, independently in 1896. Okay. But what inequality we will use for this algorithm kind of is this. So with respect to x over log x, this is base 2, pi x is at least x over log x. So what is the probability that I pick a prime when I sample uniformly at random from 1 through x? So pi x is at least x over log x, right? Divided by x. So 1 over log x is the probability. This is at least, like it is a lower bound on the probability that I pick a prime when I do one sample between 1 through x. Okay, and if I want to ensure that there are some k primes between 1 and x, then it is suffices to set x which is at least 2k log k. So ceiling of this number 2k log k, it suffices. Why? Because if I look at the value of pi x, then because x is more than 2k log k, and this is an increasing function, as you increase x, the number of primes just increases. So that is at least pi 2k log k. And if I just plug in the lower bound on, so this has to be greater than, actually, sorry. If I kind of plug in this inequality here, then I get k times 2 log k, I'm just rewriting this, divided by log of this, which is log 2 plus log k plus log log k. But this quantity, the denominator, is at most 2 log k. Okay? So this is at least k. And kind of we will use this fact in the algorithm. So if I want to ensure that I have some 100, I want some 100 primes at least in my range, then I set x to be 2 times 100 log 100. Okay? Okay. Now string equality problem. So a small story behind that. So let's say we have Alice, who is a captain of a Mars lander, and she has some n-bit string x. And Bob at mission control has a string y. And they know nothing about each other's string, but they want to compare. Okay, that's probably part of their mission, whatever. They want to compare whether x equals y or not. Okay? Now this n could be very, very, very big. Like say Wikipedia, they want to compare their Wikipedias. They have copies of Wikipedia, they want to compare whether they are same or not. Okay? Now, one possibility could be just Alice sends x and Bob confirms whether x equals y. We are not assuming any communication errors. If Alice sends x, Bob gets x, exactly. Okay? So, but then you have to, Alice has to send n bits, which could be very, very costly because it's coming from Mars. Did you see recent pictures of Mars in news? They are very beautiful. You should go and see it. So probably, yeah. So it may be really costly. So what they want to do is share less communication as less as possible and still check this equality. Okay. So if they want to be sure, 100% sure whether x equals y or not, then there is no way to do this with less communication. You have to send all n bits. But if you are fine with, like, let's say 99.99% surety, then you can do log n directly from n to log n. That's a huge jump. Okay? And what do I mean by like 99.99% surety? There will be one-sided error. So if x equals y, then probability that Bob says equal is 1. We will design such a procedure. Okay? But if x not equals y, then probability that Bob says unequal, that's the right thing, with probability is 0.9999. Okay? So with 0.0001, it can still say equal when x not equals y. So it's a wrong answer. But wrong answer with very, very, very tiny probability. Okay, so maybe that's okay. Right? If you have to gain something, you have to lose something. Right? And it's okay if you are losing very, very tiny thing. Okay, so how do we do this? So remember, we just discussed that if we want some kind of k number of primes between some number 1 through m, then setting m to 2k log k is enough. So let's say k is 5n. And we'll see why we are setting this 5n. Okay? So let's set this m to 2 5n log 5n and ceiling of that. Okay? Now what Alice will do is it will sample a prime between 1 through m, uniformly at random. Okay? Then it will compute this hash function, which is just hp of x, which is x mod p, and send prime p as well as hp of x and not x. How many bits is she sending? So she's sending two numbers, p and hp of x. How many bits? Log m bits. In fact, 2 log m bits. Right? Because both p and hp of x are at most p. And p is at most m. Right? So she's sending two numbers which are at most m, so 2 log m. And then Bob checks whether, so he can compute now hp of y, right, because he has p. And then compares whether hp of y that he computed is same as the another message he got from Alice, which is hp of x. And he says yes equals if he finds yes for this answer, this equality. Otherwise he says unequal. Now what one-sided error could he make? Can he say unequal when x and y are equal? No, right? Because if x and y are actually equal, then hp of y will be hp of x. And he will correctly say yes, equal. Right? But it may happen that x and y are not same and still hp of y equals hp of x. And then that's an error. Right? So strings were unequal, but Bob said equal. But what is the probability of that happening? Okay, and we will kind of say that it is at most 1/5. Now, before we go into the proof, I want to give an intuition. Okay? So why this is at most 1/5? Actually, there is this relation with this 5n here. It has to be, right? There's a pattern matching there anyway. Right? So suppose x naught equals y. But you see that hp of y equals hp of x. That means x mod p equals y mod p. What does this say about difference x minus y? Absolute value of x minus y. It has to be multiple of p. Right? So p should divide the difference between x and y, if that happens. Right? So this, now look at this difference and look at all the divisors of this difference. If I bound that the number of divisors of this difference are at most n, then do I get this probability? So first of all, the difference is at most p. Right? So it is at most m. So all the divisors have to be less than or equals m. Right? So it has to be a prime in this range, in this set. Now I'm saying that there are at most n divisors of this number. Okay? And there are total possible 5n primes. So there are n primes out of these 5n primes that may divide this difference. Then what is the probability that a particular prime that I picked uniformly at random, that will divide this number out of this 5n? It's n over 5n, so 1/5. Okay, this is the main intuition. You have to look at the difference. So let's try to prove that. So the probability that Bob says equal is same as probability that when x naught equals y, but probably hp equal x equals hpy. And in general, we will have, instead of 5, just say let's s some number s n log sn, and we want to bound this probability to 1 over s. Okay, I just replaced phi with s, some number. Okay. So again, if this happens, that means x mod p equals y mod p. So let's look at the difference d between x and y. It has to be the case that d mod p is 0 because of this this equality, right? And also that d has to be at most 2 to the n. Why? Why is that? Why d cannot be more than 2 to the n? Remember, x and y are n-bit numbers. So what is the upper bound on x and y? 2 to the n, right? So the difference cannot be more than 2 to the n. So this gives us a trivial upper bound on d. And let's say we look at the prime factorization of d. Now each of these factors has to be at least 2. And there might be repetitions here. That's okay. Okay? Then we know that because every factor has to be at least 2, d has to be at least 2 to the k. Because you could have, like this is lower bounded by 2 times 2 times 2 up to k. Right? So you got an upper bound which is 2 to the n, a lower bound which is 2 to the k, and k is also the number of factors, different prime factors of d. That means at most k primes can divide d. Right? And we, from this inequality, when if you put these two together, you get 2 to the k is at most 2 to the n. That means k is at most n. So the number of primes that can divide d is at most n. The possible primes from which you are picking, there are at most 5n, at least 5n of them, or Sn of them, right? So the probability that you picked a prime, which is one of these prime factors, is just n over the number of primes before m, which is just, you can simplify to be 1 over s when you replace what is pi of m, the upper bound formula and pi of m. Okay, questions? Are you comfortable with this modular arithmetic? What do we mean by x mod p? What is x mod p? Yeah, when we divide x by p, the remainder is x mod p. Okay, so why do I get that d has to be divisible by, d mod p should be 0, that means d has to be divisible by p? Because the remainder is 0, right, when we divide d by p. Because here you are saying that when you divide x by p and y by p, the remainders are same. Okay. Okay. So we get 1 over s as the error probability. If I want to make it 0.00001, there are two ways to do it. So far we just got 1 over 5 when we set s equals 5. We can set s equals, let's say, 1 over 10 to the 6 or 10 to the 4. Sorry, s equals 10 to the 4. And then 1 over S will be 0.0001. Right? As we wanted, a very low probability. Or we can repeat the process. We can set S to be a very tiny number, say 2 or 5 or whatever. And then let Alice send not only one time, but R times. Every time picking a different hash function. Okay, so Alice repeats this process of picking up prime P, computing HP of X, sending P comma HP of X 10 times, say, or say R times. Okay, then every time the error probability will be at most 1 over S, and these are independently at random. The primes are picked independently at random. So the error probability will be 1 over S to the R. So what should Bob do in this case when Alice is sending so many primes and hash? So the procedure is clear in the second possibility. So Alice sends, say, computes samples P1, first prime, computes HP1X and sends P1 and HP1X. Then she samples P2. So Alice samples P1 and sends HP1X. Then she samples P2, sends HP2X, and so on. And she does this, say, 10 times before hearing back anything from Bob. Now what should Bob do? What if he just checks? So this is what Alice did. What if Bob just checks HP1Y equals HP1X? Can he do this? He can do this because he has P1 and he has this and he has Y. So he can do this computation. What if he does only this? We just proved that the error will be, if X equals Y, he will rightly say equal. If X not equals Y, then he wrongly say equals with probability at most 1 over S. Right? Now if he does not only this, but also checks this. Now what should he do? So he has yes, no answer for both of these questions. Suppose he gets yes and yes. What should he say? Probably yes. Right? Because there is no other possibility for him. If he sees, say, no and no, then he should say no, right? If HPX not equals HPY, then definitely X not equals Y, right? If he gets no and yes, one no, one yes, no, right? As we just said, if HPX not equals HPY, then definitely X not equals Y, right? So what is the probability that X not equals Y, but for both of them you get yes and yes? 1 over S to the, yeah. So for this too, it will be 1 over s square. Right? So he can do all of these comparisons. And say yes if, or say equal, sorry, if all are yes. I think this is an important point, and that's why I'm stressing it, that if you have one-sided error and you have some kind of independence, you can actually push the error to a very, very tiny number by repeating the process. Okay? And if you have, say, s equals 5 and r, if you repeat it 10 times, then 1 over 5 to the 10 is really, really small actually. Okay? Now, how much communication did we do? Let's put things into perspective, right? So, m was this number, and in each round, we just discussed that there are 2 integers that Alice is sending. Each integer it at most number m. So you can represent each integer by log m bits. So 2 log m bits in each round. If you take a log of this number, that is at most 4 log s plus log n. So in the above 2 procedures, as you increase s, you're kind of increasing the number of bits that you are sending. But if you increase the number of rounds, also you are increasing the number of bits, because this is, in one round you send these many bits. Okay? So if we have, say, x and y as 2 copies of Wikipedia, as we kind of started with, then there might be, say, about 25 billion characters. Each character, say, 8 bits. Then n will be approximately 2 to the 32 bits. Okay? So the first naive procedure was just sending these 2 to the 32 bits. What if we do this procedure 10 times? The second approach. Right? With s equals 5. Then the number of bits you can calculate is at most 1280. So that's a huge improvement from 2 to the 38 to 1280. Okay? So it is very powerful. And the error probability is like really, really tiny. Okay. Now let's come to our main question, the algorithm for pattern matching. So here, let me repeat what was the question. We had a long string T of length m, say, and we have a small pattern P of length n. And we want to check all the occurrences of P in T. We want to compute those. At what positions does P occur in T? So for example, suppose we have T is a abracadabra, okay, and the pattern is AB. What positions does P occur in T? Let's say the positions are 1, 2, 3, 4, so on. It occurs at 1, right? Here we have AB at the first, starting at first position, and then we have AB here, right? So it's 1, 2, 3, 4, 5, 6, 7, 8. So the output should be 1, 8, and then there is no more. So the question is clear. We want the positions of all occurrences of P in T. Okay. Okay. So before we start designing the algorithm, let's define this notation So T sub I, so let's take two numbers j and I, j greater than I. Then a substring between position I and j in T, we will define it by Tij. So T I dot dot j is just a substring of T which starts at I and ends at j. Okay? So what would be a naive algorithm? Order Mn algorithm, brute force algorithm to do this task. No dynamic programming, no hashing, nothing, just comparison.
Check every pattern for every index.
Yeah, exactly. You go to every index and starting from there, check whether P is that substring of length n starting at that point is same as P. Right? So at every index you go, you check, you take this substring of T starting at that position of length n and check whether that is same as P. If that is, then put S into I into S and so on. Just do it. And it is order Mn because the number of times you run this for loop is order M times. And in every step of the for loop, you are doing n comparisons because P, length of P is n. So order Mn. Now suppose I want to do something fancy. Okay, and instead of doing comparison, direct comparison, I would compute a hash of these patterns and the substring and compare the hashes. Okay, so let's say I'm picking P uniformly at random between 1 and M. I'm going to fix M later based on the guarantees I want. Okay, and let's say HP is our old hash function x mod P. Then instead of comparing those substring and the pattern, I'll compute the hash first and then compare the hash. Did I gain anything? So comparison wise, yes, because both of these numbers, if M, capital M is small, both of these numbers may be smaller than N. M log, so that will be, sorry, so I have both indices, right, small m and big M. So small m times log big M. Right? But it so happens that if I want to find this hash for an n bit length string, then it does take order n time. Okay, so before I do this comparison, I have to compute these two hashes, and computing those hashes will take order n time. So again, my running time will be order m times n. Right? Because in each for loop, I have to compute these hash. Even if I store HP, the hash for the pattern, I have to recompute this hash for the substrings as the I change. So at least one hash computation per for loop. Right? So the question is, can I do better than this? Okay, so how can I do better? In what sense? Right? Because I want every occurrence of the pattern, I have to go through all those indices and look at those substring at all those indices. Right? But maybe because when I go to I plus 1th index, I already have done ith index. And maybe I can use the hash at the ith index to compute the hash at the I plus 1th index. Suppose I can do that. Suppose somehow, magically, I compute the hash of the substring at I plus 1 using hash of substring at I in order 1 time. Then what time does my algorithm take? M. Right? And to start with, I may have to do this hash of the p, which will take order n times, so m plus n. Right? So initially I start with computing hp of p and hp of t1 through 1 minus 1 plus n minus 1. So those two hashes, which will take order n time. And then every time in the for loop, I'm taking order 1 time. I'm running the for loop m times, order m times. So that is another order m, so order m plus n. Right? So, but how do I do this? How do I compute hash at I plus position I plus 1 using hash at position I? Okay, and we will do this through rolling hash. This is a very interesting concept actually. Okay, I find it very fascinating. So what does it say? Suppose I have these two strings, x and x prime, and the x is the substring at I, and x prime is a substring at I plus 1. So one example, so how do they look? There is a lot of common bits between x and x prime, right? So suppose x is this pattern, 1 0 1 1 0 0 1, then x prime you get by shifting x one bit and adding a bit at the end, right? So you discard the most significant bit, highest bit, and you add a bit at the end. So possibility for x prime is 0 1 1 0 0 1 0 or 0 1 1 0 0 1 1. So you add a 0 bit or a 1 bit at the end. In this, we will use this commonality to compute the hash for x prime from x. So how can I write x prime in terms of x? So what did I do? First, from x, I have to discard the highest, most significant bit, right? So I kind of subtract this quantity, which is, what is that bit, times 2 to the n minus 1. If that bit was 0, I do not subtract anything and I'm fine, right? If bit was 1, then I make it 0, basically. Then I multiply by 2, that is shifting by right. Right? When I do this shift by right, I'll have a 0 bit at the end. So I can add the last bit of x prime there to make it 1 or 0 based on what x prime has. So this computation is clear of x prime from x. Right? Now we want to do mod p. So suppose I have x mod p and I want to compute x prime mod p. So let me apply x prime mod, like mod p operation on this expression. Okay? So x prime mod p is exactly, when I apply a mod p here, it pushes inside and you get 2 times x mod p minus this bit, highest order bit of x, times 2 to the n, because I multiplied 2 inside, 2 to the n mod p plus x prime LB, lowest bit is 0 or 1. If I do mod p, it will remain 0 or 1. Right? Because p will be at least 2. So x prime LB. And then you have to do mod p. Because when you do, like the number has to be, final number has to be at most p. Okay? And this first quantity is exactly hp of x, that's a hash of x. I can keep and compute and keep this hp of 2 to the n. Okay, that's repeating, kind of. Okay? And then I have to do this summation. So if I have these two numbers, then how much time does it take? So suppose I can do addition, multiplication, subtraction in order 1 time for log m bit, for log m bits, numbers. Then this arithmetic I can do in order 1 time. And because this number will be at most order p, which is at most length log m, so I can do this mod p also in order 1 time. So you see the, at least the simplification, right? That instead of computing entire x prime mod p, I can do this summation if I have hp x mod p and 2 to the n mod p, and then I have to just do mod p after doing this summation. Right? So that's exactly we will do. That's called rolling hash. And assuming, so we'll see that. Okay. So you compute a priori a hash of the first string, substring, which is starting at 1, the hash of 2 to the n, and the hash of pattern p. These three we compute a priori in the first step. Okay? Then we go inside the for loop, do the comparison for I equals 1. We can do that because we have both the numbers computed. Right? And then just put it inside S if they are equal, otherwise not. Then we compute HPT 2 to the 2 plus n. Sorry, 2 to the 1 plus n. And I can do that. So string at 2. Now I have to compute the hash for string starting at position 2. I have hash for string at starting at position 1. Using rolling hash, I can compute this hash for this next string, as we just described. Right? And so this is it. Right? We don't have to recompute this hash for the next string entirely from scratch. We can use the hash from the previous string. Okay? And we will see why the running time is what we want. So in the first step, we are doing 3 hashes of n-bit strings. So that's order n. It's actually order 3n, right? This order n. Then in each for loop, suppose I can do log m bit arithmetic in order 1 time. Okay, so I have a super big computer whose each register can store log m bits. So I can do this log m bit arithmetic addition, multiplication, subtraction, division in order 1 time. Then can I compute this in order 1 time? Yes. What is the size? Why? Because what is this? What is the maximum value of HP of x? It's m, capital M. Right? What is the maximum value of HP of 2 to the n? It's capital M again. Okay, because P is at most capital M. So this entire number is at most kind of 2 times M. Right? And that length is log M. So because I can do log m bit arithmetic in order 1 time, I can also take mod P in order 1 time. Because both numbers, the number inside this and P has log m bits. Okay, so this tells me that both the steps of the for loop I can do in order 1 time. That's what we wanted. So overall it's m plus n time. And we will see why this log m bit arithmetic, this assumption is not too bad. Okay? So first of all, before we go into that, I want to talk about error. How much error do we make? Is the set we compute S correct or wrong? So do we have all the indices where the pattern is matched in set S? So suppose I have a match at ith position. Will I be there in S? Yes, right? Because when I compute, when I do this, if Ti, this substring is same as P, the HP of this will be same as HP of P. It will say yes, and that's why it will put I inside S. So all the pattern positions where the pattern is matched are there in S, right? But can it have more indices where the pattern is not matched? Yes, right? Because there may be a case that the substring is not same as P, but the hash values are same, right? But what we want to kind of bound is what is the probability of this happening? What is the probability that there is no match at some position I, and still we see that when we take hash, they are same. Okay? If we can bound this, then we can apply union bound and bound the entire probability of getting any wrong index in S. Okay? So I'm going to set M to this number 2Sn log Sn, and then because this x and y are of length n, the probability that when x not equals y but hpx equals hpy is at most 1 over s. This we already saw in string equality, right? So what is the probability that I get at least any index I which is not actually a match? Okay, so for any particular substring, if it is not same as the pattern, then the probability and the probability of getting I in S is at most 1 over S, which is this probability is same as that probability, right? Where X is just this substring and Y is just P. Okay. Now there are M such substrings, at most M such substrings. So what is the probability that for any index that we have in S, for any of these I's, there is no pattern match, but we have I in S. So we have that index wrongly in S. For any particular index, that probability is 1 over S. There are M possible indices. What is the probability that any of them is wrongly put in S? Is this like completely going above the head? Look, I mean, I can keep teaching and I can keep talking, okay? If it is not useful, then we are wasting my time as well as your time. Actually, more of your time. Because so many students, right? So you have to ask questions. If something is not clear, stop me. We don't have to finish everything. Okay, finally you can go back and see the slides and maybe you will be able to figure out if you can understand the main parts. So what's not clear? Why? So suppose I tell you that this probability is at most 1 over S. Then what is the probability? So is the question not clear that any index in S is wrong? So let me rephrase the question. You have lots of indices in S, right? What are all possible indices? How many of them are there? M. What is the probability that I pick an index in I and it's a wrong index? 1 over S. So if there are M possible indices, what is the probability that any of them is wrong? There exists a wrong index in S. Sorry? Okay, so let me write this probability again. So this is for all index I in S, right? So I can say by a union bound, this is at most, okay, let me do with equality first. Exactly what that is. So this is equals probability union for any index I in S, I is wrong. Agreed? Right? I'm just rephrasing this, whatever I wrote in text, in somewhat math. By union bound, this is at most summation I in S, probability that I is in S, Now what is the bound? M over S. Because there can be at most, the size of S is at most M. One more, yeah. Right? So then what is the probability that S is correct? It's completely correct. There is no wrong index in it. 1 minus M over S. Right? And if I want that to be 0.99, I want 1 minus M over S to be 0.99. Which means I want M over S to be 1 over 100. And that gives me S should be 100M. So if I set S to be 100M, then I'm good. But if I do that, then assuming that log M bit arithmetic can be done in order 1 time 2 ridiculous? I cannot do that probably. So let's see whether that is okay or not. Okay? Because when I plug in this value of S there, maybe this M becomes too huge and then log M is is too big to do those arithmetics fast in order 1 time. Okay, so this M will be then 200 mn log 100 mn. That means this log M will be order log small m. Now here order is hiding, say, I think a linear term. Not a linear term, linear and log m term. Okay. So now let's say T, as we started, is entire Wikipedia. And we kind of had counted the number of bits roughly to be 2 to the 38. And let's say my n is not too big, but it could be order of 2 to the 16 or something. Then if I put in all of these numbers here and count log m, it will turn out to be around 64. Which is not bad, right? We have laptops with 64-bit CPUs. Right? So that's okay, it's not too bad. So it's not a ridiculous assumption. It's okay. Okay, questions? This finishes the algorithm and the proof. Yeah?
Why can't we repeat while we do each comparison to reduce the error?
Sorry?
So when we compare whether a pattern and a substring are the same, why can't we also do the repetition?
Good point. Yes, you can do that. And that will reduce the error. So what she is saying is, instead of doing this one comparison, why don't we kind of keep track of 10 hash functions and 10 hash values, some constant. Okay? And every time do this comparison for all 10, and if we say get yes for all 10, then only we put the index in S. That will reduce the error exponentially fast. Okay? You have to do some more computation every time you have to do this 10 rolling hash and everything. But that's okay. You can do that to reduce the error. Okay. Any more questions? Okay. So all in all, so this is kind of finishing hashing in some sense. So hashing is powerful and important technique. Okay. It is applicable in many practical situations, and it is also kind of randomization is fundamental to understanding hashing, because you are reducing the size of the object, so you have to lose somewhere, and there is some error probability because you are using some randomization, but you can bound that, and actually you can do good hashing in practice. Okay, and it is useful. And as we saw, it is not only for storing data, but it can be useful for even algorithms. Okay? So I think this is a useful concept for theory and practice both. Okay, that's it. Yeah, next lecture is a review session. And so we are trying to, so generally the typical review session is like a professor comes here and you ask questions and he or she tries to solve it here, right? That's how it is done generally. I'm thinking of doing a bit differently, like if the TAs agree, then we all three be there, 2 TAs and me, and we try to solve as many questions as possible, like individually. I feel that if I solve the problems here and not many of them have questions in those problems, it is wastage of a lot of time. So I'm thinking of doing a big office hour. Do you think it's a good idea? Or you prefer the old style?
How would that work?
So suppose we three are there, then you could have, we could have a queue or something, and each of us are individually kind of answering questions for all of you, one by one. Do you think the old style is good? New style? No? Okay. Okay, we'll see. It's like a split, so we'll see. Yeah.
So this is the max ping